Okay, hi everyone. So, another video this time on vectors, M1 vectors. Now, some of you would have done a lot of vectors work at school, and some of you really would have done virtually no vectors work at school because you wouldn't have needed your graded, uh, for your grade C equivalent. You know, a lot of schools are aiming just to get that grade C and above to help their score figures and stuff. And vectors is a higher tier A star kind of topic, so some people wouldn't have been exposed to that work before. Even if you have, this is gonna, I think this part is really important, going through the abstract use of vectors before we start launching straight into the M1 vectors. Because if your vector theory is good in M1, then it will be much more smooth. So it'll be a lot smoother when you go into C4. Okay, so what is a vector? How would we describe a vector to someone who doesn't know what it is? Well, I like to think of a vector as an instruction, an order. So the classic definition of a vector is a quantity or a magnitude. So a magnitude, i.e. a quantity or a length with direction. So like I say, I like to think of that as an instruction. If you imagined that we were in the South Downs, uh, you know, we all had walkie-talkies, we were orienteering, or we were in the TA, the army or something, okay, and the general says, I want you to go 100 miles north, okay? Say if someone else over here had a walkie-talkie, they would also hear that instruction. So can you see that instruction, 100 miles, go 100 miles north, can be applied anywhere. You know, this should help with the confusion of, well, why can I just put a vector over there, let's say, or over here? Well, because a vector is an instruction. It's a quantity with a direction, which you can apply anywhere. If this person heard it, they could go this way. If this person heard it, they would go this way. Do you see? It doesn't matter where you are, you can apply that go 100 miles north anywhere. And the same thing works for forces, doesn't it? So forces can be described by a vector. Apply 100 newtons southwest. So if that's south, that's west, southwest will be there, wouldn't it? So apply 100 newtons southwest, you see? Vectors are, you can describe lots of things with vectors. So that's what a vector is. And let's think about our basics when it comes to vectors. So, for example, if you had a parallelogram, okay, and this here was described as the vector A, and we've got points. So if someone told you a parallelogram ST, ABCD, STUV, yeah, STUV, you would always go anti-clockwise when you label your points, your vertices. So vertices are also called, are the same as points or nodes. And vectors, so just some notation here. If I wanted to go from S to V, my notation would be S to V with an arrow on top, okay? That means go from the point S to the point V, which you'll notice is also described as this vector A. And A is this line here, isn't it, with a direction, do you see? So this A can be applied anywhere. I can apply it here, I can apply it down here. As long as the direction and magnitude is the same, that is represented by the vector A, okay? So vectors in small cases, from point to point, that's in capital letters, okay? So imagine if I drew this shape, this parallelogram, okay? I've only defined two vectors, haven't I? I've defined A and I've defined B. So A is that kind of go northeast direction, and B is just go east direction. So how would I get to certain things? S to T, as we've defined, if I want to go from S to T, I would go via B. But what would the vector v to u be? How would I describe v to u? Well, hopefully you're screaming out to the video and you're saying, well, v to u is parallel to s to b. So I'm just applying the vector b to it, aren't I? So this vector here must be b. Do you see? Exactly the same as s to t. Likewise, t to u would be the same as applying a, wouldn't it? If I applied a at t, I would get to u. What if I wanted to go u to t though? So u to t this time. Hopefully again we're screaming out at the video. This is the same magnitude as a, but in the opposite direction, isn't it? I'm going backwards, so this would be described as minus a. So if the arrow is going in the opposite way to its original, it would be described as negative, that vector, so minus a. Likewise, if I wanted to go u to v, that would be the same as going minus b. Okay? Hopefully we're getting the idea then. If I wanted to go this time from s to u though, and notice I could draw that as an extra vector, which I have in green. I can only use though the vectors that I know, which are a and b. Okay? How do I get from here to here? And if you imagine these vectors, these are like roads. These are the available roads to us. Okay? How do I get from S to U? Hopefully, again, you're saying, well, first I need to go from S to V, don't I? So that's A. And now I'm at V, I can go along B to get to U. So that would be described as A plus B. Do you see? What was if I wanted to go from T to V? Well, T to V, I could go T to U, which is A, and then I could go from U to V, which would be minus B, wouldn't it? So A minus B, as B is going in that direction. Do you see? Hopefully you're starting to get the idea of that now. Now, let's start applying this to abstract problems. So it says here, OABCDE is a regular hexagon. So hexagon, six sides, sorry. And if we draw it, and remember, we go anti-clockwise, so O, A, B, C, D, E, right? There's our hexagon. It should be a regular hexagon. My drawing's not that great. Maybe we can make that a bit nicer. Yeah, a little bit more even that way. Okay. The points points A and B have position vectors A and B. So A, and remember position vector. As soon as you hear the word position vector, that means relative to an origin. Okay? So this is our origin O. O is always the origin. So it's saying O to A is described as A, right? But then it's saying that vector B is referred to the origin as well. So B is not A to B, it's O to B, okay? Because it's a position vector. And this is very important that you understand what a position vector means. As soon as you hear that word, it means relative to an origin. So O to B is described as B. It wants us to find in terms of A and B the position vectors. So as soon as I hear position vector, I'm thinking, O to C then, O to D then, and O to E then, right? It wants these position vectors in terms of A and B. Stop the tape if you want to have a go. Okay? Stop the tape and give it a go yourself, and let's see if we match up, just to see if you understand. So do that now. Okay, if you have no idea what you're doing, or you've had a go, and you want to see how we do it, then let's do it. So I need to come up with ways of expressing O to C, O to D, and O to E. Well, there's lots of ways we can do this. Um, One property though that you probably would like to know or need to know, and maybe some of you do know, is that from vertex to vertex, so node to node on a hexagon, this green dotted line is twice the length of a side. Okay? So all opposite pairs are twice the length of a side, right? So what I'm saying is that O to C is the same length as two lots of E to D, two lots of this, right? So that helps, doesn't it? Because if I want to find O to E, for example, here's O. First I need to get to B, don't I? So O to B. So first O to B is B, which we knew. And now I need to go backwards twice the length of this O to A. But remember, the vector A is going O to A, but we need to go backwards. So one that way, and then one that way. So this is going to be minus A minus A. So B minus 2A. Do you see? Okay, cool. That's that one down. Next, if we want to do O to D or O to C, how would I do O to E? To D, sorry. Well, think about it. I've just found the vector O to E, haven't I? I've just found this one, O to E, which was described as B minus 2A, remember? Remember, you can apply a vector anywhere. So if I want to find, for example, O to C, doesn't matter. O to C, so I'll draw that in. That's what I'm trying to find. If I first go to B then, B, so B, and now I want to go from B to C, which is parallel to O to E. So I can go plus the same as O to E, which we just found out was B minus 2A. So this is 2B, subtract 2A. Yeah? Fantastic. Sorry, that was O to C, wasn't it? Not O to D. So O to C. And now I want O to D. Well, how do I get from O to D? Well, again, you should be screaming at the video because if I follow O to C again and then I go backwards, that length O to A, but it's in the backwards direction, isn't it? That's the same as minus A. So if I go O to C first, minus A, I know that O to C is 2B minus 2A, and now I've got minus A again, so that gives me 2B subtract 3A, and it's done. Next. Oh, a bit harder this time. So again, we've got an origin, so we're thinking position vectors. So it says again, pause the tape if you want to, okay? In triangle OAB, M is the midpoint of OA, and N divides AB in the ratio 1 to 2. So if we know anything about ratios, that's saying there's 3 parts, and A to B takes 1/3 then, one of those parts. So this from N to B must be 2/3 of A to B, mustn't it? There's A, there's B, yeah? And A to N must be 1/3 of A to B because of that ratio given, okay? M is the midpoint of OA, so we know that's there. Given OM is A, so let's draw on our vectors. O to M is A, and remember O to M is the midpoint of OA, so therefore this vector here must be A as well. So actually O to A is not A, it's 2A, isn't it? Okay, so we should write that down. O to A we know is 2A now, right? And O to M we're saying is just A. O to B is B. So there's B. So find ON in terms of A and B. Well, like I say, it's always good to map out your trajectory. So I want to get to here, don't I? So that's the vector I'm trying to find. How do I get there? Well, it looks like I need to go from O to A and then down this way, don't I, to get to N. So let's map that out. Let's say that O to N is the same as O to A, which I already know, plus A to N, which, aha, I kind of already know because I wrote that here. Do you see? So O to A must be two lots of A, which was written here, plus A to N, which we've put there, is a third of A to B. But what's A to B? How do I get from A to B? Again, let's get this thing going. A to B. And this rule is going to hold for all the time. So A to B, using the vectors I know, well, I need to go down here, don't I? But A is going this way, so this must be minus 2A. I'm going in the opposite direction to the arrows. And then I go to B, don't I? So plus B. Okay? So 2A, and if I multiply that bracket out, so a third times that, so that's a third B minus 2/3 A. So I'm left with, what's that, 4/3 A plus a third B. And that's O to N. And we're happy. Last one then, last example. Here's where it gets much tougher, but again, do you understand what's going on? So given P to X, this is P, this is X. There's no origin here, so they're not position vectors. Equals KP to R. Okay. Find K. Difficult. What's it even mean? It's saying, given that P to X is parallel to P to R, if vectors are multiples of each other, then they are parallel to each other. Do you see? P to X is here. P to R is the whole thing, and this is just one continuous straight line. So it's saying that K is a fraction of P to R. We need to find out what that fraction is. Difficult. Difficult. Or is it? Let's think about it. So, we know, again, pause the tape if you want to do it yourself, but this is definitely a good one to talk about. So P to R. We know that P to R, how do we get from P to R? So P to R, what is P to R? P to R is, we know, P to Q, so that's 3A, plus B. That gets me to R, doesn't it? And we know that P to X from here is a fraction of P to R. So this is K, lots of 3A plus B. That's helpful, isn't it? Now, what else do we know? Well, we know that the diagonals cross at X, don't they? They cross at X. So we've worked with this diagonal. But what about this diagonal? This diagonal crosses at X, doesn't it? And that maybe if we can intersect them somehow, we can find out what that proportion is, right? So S to X must also be some proportion of S to Q, surely, from the same logic as what we had up here. S to X must be some proportion, let's call it mu, of S to Q. It must be, right? And how do we map that out? Well, S to X is the same as, well, S to Q, sorry. Let's go for that. So if we go from this side. So S to Q, just like we did before, is the same as, well, it looks like I can go from here. So 4A up B, so that's minus B, isn't it? There we go. There's S to Q. And we know that mu S to Q is the same as S to X. So S to X must equal mu S to Q, which is mu lots of 4A minus B. Okay, so S to X and P to X intersect each other, don't they? Yeah? They intersect each other. So it makes sense to me that we need to have two versions of p to x. So if we can use what we already know to come up with two versions of p to x, then they must be the same, mustn't they? Okay? So if we already know then that p to x from our first definition is k lots of 3a plus b. Sorted. What's another version of getting from p to x though? So we've done the direct way, but we could also go this way, couldn't we? We could go p to x is also the same as 3a, which is p to q, and then back some proportion of q to s. Well, we know that q to s, but s to q is 4a minus b. So therefore q to s, if I'm going the other way, is to times everything here by minus 1, isn't it? So this is b minus 4a, yeah? But we want to go some proportion of q to s in order to get to x, don't we? So this must be plus some proportion. So this, it doesn't really make sense to use mu actually, because mu in this case is s to x, but we want q to x, don't we? So it's not going to be the same proportion. So let's call it lambda. Hopefully that isn't too confusing. Lambda q to s. And q to s, as we've just said, is b subtract 4a. Okay? So what I'm doing is, and this will always work for this kind of problem, is I'm just coming up with two different ways of getting from one point to the other point. And therefore, these two things must be equal to each other. So if we go for that, we're saying, if we make this one down here, we're saying k lots of 3a plus b. So if I multiply that out like this, that's 3ka plus kb. Yeah? This must equal the same as 3a plus, and then multiply this out, lambda b minus 4 lambda a. So can you see it's not obvious that the stuff that's the coefficients, the coefficient means the number next to, right? The coefficients of a must be the same as the coefficients of a here. So the coefficients of a, if I kind of factorize to make it more obvious, if I put all the stuff with a at the front on the left and on the front on the right, can you see we have, whoops, that's b. We have the 3a from here, and we have the minus 4 lambda from here, plus, and now b, our only factor is lambda. Can you see? So if I compare a's with a's, I can see that 3 lots of k must be the same as 3 minus 4 lambda, right? And I also can see, if I make this b, sorry, here, that this right-hand one for b must be the same as this right one here as well. So you can see here that k must be the same as lambda. So now you've got a simultaneous equation. We're trying to find k, so let's replace lambda with k. So here we've got 3k is 3 minus 4 lots of k, and therefore 7k is 3, and therefore k is 3 over 7. Okay? Hopefully that's made sense. Go through it again if it doesn't make sense, right? You've got plenty of time in the holidays, so there we go. That's it for abstract vectors.